our job in this lesson is quite simple, okay? We are going to have a look at positive and negative ions, so this first pointer here, and how they are formed by the loss and gain of valence electrons. Now, all of these other things will come with time and they'll come with practice, but the key idea today is this one. We are looking at how positive and negative ions are formed and how it involves the loss and or gain of valence electrons. So, let's fill in the blanks together. Atoms, the things that we've been speaking about so far, are electrically neutral. This means that they have no charge. They are neutral because they have the same number of positive watts. What are the positive parts of an atom called? Excellent. They are the protons. And they have the same number of protons and? Electrons. Fantastic. Well done. Okay. Now, these electrons, as we learnt yesterday with our friends the noble gases, so group 8 running down in green on our periodic table in the room, electron shells are most stable when they are full, okay? When they have a complete valence shell. So when we're talking about these ones here, I'm going to highlight it in purple, group 8 elements, okay? Everyone wants to be the same. Everyone wants to achieve the same electron configuration as the group 8 elements. So when they're full, they want to effectively be like a noble gas.
What if they win the lottery? Then can they be a noble gas?
Sure. So everyone wants to be like a noble gas, all right? They all want to achieve the same configuration. Now, we learnt what the configurations were. So helium, for instance, has how many electrons in its outer shell? 2. Neon, okay, our next element down after helium, has how many in its outer shell?
8.
What about our next element down? Argon?
8.
8. And that is our 2-8-8 rule. Okay? The 2, you're right, does come into play when we talk only about potassium and calcium. Okay? So, many atoms do this, and here's the key idea again, by gaining or losing electrons from that valence shell. And when it happens, it is going to form what we call an ion. An ion is a charged particle. It's not like an atom, which is neutral. An ion is an element that is something with a charge. Okay? It is not neutral. So, this next part is really important, but it's actually done way better down the bottom of the page. So we'll read it again and we'll highlight it there. But we're just going to read right now. Metals have their last electron shells, their valence shells, almost empty. Okay? And therefore, they lose those outer electrons. Okay? And we'll talk about why that is in a second. Non-metals, on the other hand, okay, have almost full valence shells. And so they find it easier to gain electrons. And so what we're going to do is, rather than have a look at this diagram here, okay, I'm actually going to draw a slightly different variation, and I'm going to draw it quite small so that you can copy it as well, because I don't think this diagram is particularly the best one at showing these electron shells. We had a question up the front though. We'll come back to it. Silicon is something quite unique because it's +4 -4. It's quite fun. So when we talk about this, we're all going to do it together. We're going to start by drawing sodium. So how do we draw the electron configuration for sodium? Well, we need to figure out first, how many protons does sodium have as an element? 11. So we're going to start, and maybe I'll do it over on the left-hand side of your page, down the border. I'm going to draw a really small Na. And instead of representing the electrons with a E negative symbol, I'm just going to draw them as crosses today because it's going to be quite small. In our first shell of sodium, how many electrons are there? 2. Remember the 2-8-8 rule. So, 2 electrons. In the second shell, how many electrons are there going to be? 8. So I'm going to draw 8 electrons. And in the final and the outer shell, how many electrons will there be?
1.
1. It's all by itself.
Could we do
Absolutely.
But we have to say, oh, they're electrons, and this is like.
Yep. So that's what I'll show you how to do in a second. Okay.
This is
So
like an onion.
when we're talking right now, you told me at the beginning, sodium has how many protons? Okay. So over on the left, I'm going to write 11 protons. And I'm writing it in the same color that I wrote sodium in. Okay. Just because I want to show that the protons are found in the nucleus. The next thing, if we counted up all of our electrons, so I've represented them as X's right now, I would have how many electrons in an atom of sodium? 11. Now, when I talk about these electrons, and this is where I make it really clear. So if you're in a test and you're thinking, where do I write? You can just put in brackets next to it, X, right? When we look at the charge, okay, and I always like to write the charge in green. What would the charge be in this case? If I have 11 positives and 11 negatives, it is going to be neutral. And neutral is the same as saying zero charge. It is neutral. Now, my question to you is this. How many electrons does it take to fill up the outer shell? 8. Okay. Now, my question is quite simple, hopefully. Is it going to be easier for sodium to find 7 more electrons to fill up this outer shell? Or is it going to be easier for sodium to lose that 1 electron and then have a full second shell instead? Lose the 1 electron. And so you're exactly right. That's what it does. And that's what we're going to draw over on the other side now. So I'm going to start with the same step. I'm going to draw the symbol for sodium in the center. And around sodium, if I've lost 1 electron, how many am I going to have all together now? I had 11, I lose 1, I will have 10.
Why is it not neon then?
Good question. Let's just finish the diagram and then we'll tell you exactly why. So, now we have sodium. And the reason that it is still sodium and not neon is because it has the same number of protons. And so when we're up the top here, we still have 11 protons. But what we've done now, we haven't changed the nucleus of our atom. We still have 11 protons originally, and we have 11 protons over here. The only thing that has changed is we got rid of that outer electron. And so how many electrons do I have all together now? 10. And so over here I'm going to write 10 electrons. Now, when it comes to the charge, what's the charge of protons again? Protons are? Positive, and electrons are? Negative. So if I have 11 positives and only 10 negatives, what is going to be the overall charge? Great. Positive 1. And so the charge here is plus 1. Yeah, exactly right. Question.
So really, you can identify a thing by proton.
You can identify an element by its protons.
Yeah.
You can figure out if it's an ion based on if it has a different number of electrons.
Okay.
So when we're looking, okay, we're about to introduce a word here to describe this. And while we said earlier a charged particle is an ion, when we talk about these, the charges assigned to an ion represent the number of electrons they can lose or gain to make their outer shell complete. Everyone wants to do this. Every element wants to be like a noble gas. They want their outer shell to be complete. And we refer to the charge, okay, as the ion's valency. So the charge of something is known as its valency. Now this is something that we said earlier, and I highlighted it, or I didn't highlight it, we just read through it, sorry. And it is the key idea for today. So I'm actually going to write next to it. This bit in bold is a key idea, and I'm going to draw a star next to it. Key idea. The key idea is this. Metals with only a few valence electrons will lose electrons and become positive. So when you see a metal, it is going to be positive. And when you see a non-metal, they gain electrons, and so they become negative. Okay? So metals are positive, non-metals are negative.
Is that why metals are conductive?
Correct.
So let's work together now to define this word ion. So what is an ion? It is an element, okay? Now, what's different with an ion? What is the thing that is changed?
Charge.
Great, the charge has changed, okay? So it is an element with an uneven number of what two things?
Protons and electrons.
Protons and electrons. Exactly right. So it just means that there is going to be a difference.
Is it unstable then?
It's not, because what it's trying to do is complete that outer shell. That's how it can make itself a bit stable. It can be unstable as a regular element as well though. So like sodium, for instance, the one that we've drawn just up above, is actually really unstable as a metal. And that's why it's so reactive. That's why it explodes when it comes into contact with water.
Salt doesn't explode.
Salt is actually found as an ion. It's more stable because it combines with something called chloride, and they complete each other's shell together.
Is there a way to like split them back apart?
Yes.
How?
You can provide an electrical current, or like salt, you can add it to water, and it splits away into the sodium and into the
What if I
chloride.
want to explode?
Then that's a more complicated process. Last question. Yeah.
I want to question, why does sugar explode when you put it into Coke? And the next Coke?
It's meant
Sugar or Mentos?
Yeah, well, both of it works. If you put sugar into Coke,
That's a story for a different day. Yep, second question.
and what if it was the other way around? What if it had 7 electrons, and would it just add?
7.
Great question. That's something that we're about to do in a second.
Where'd you get
Okay.
7 from?
So, everyone, what I need from you right now. All right. We are going to have a go using your periodic table. So I'm actually going to show you on my periodic table over here. I'd like to see you doing this on your real periodic table though. Okay? So, let me pause. When we talk about the periodic table now, you would have seen that in group 1, the valency, aka the charge, was +1. In group 2, the valency, aka the charge, was +2. In group 3, it was +3. In group 5, it becomes -3, -2 in group 6, and finally -1 in group 7. Now, when we talk about group 4, it was +4, -4, because depending on the situation, it can become either positive or negative. I can either gain or lose 4 electrons. Now, when we write the rule for valency in group number, it's important to recognize this. In group 1, how many valence electrons are there? 1. So I'm going to write, this is the number of electrons here. In group 2, there are 2 electrons. In group 3, there are 3 electrons. In group 5, there are 5 valence electrons. In group 6, there are 6. And in group 7, there are 7. Now, this provides our rule for us. What is the rule for valency and group number? The number of valence electrons is the same as the group number. When it comes to naming our ions, okay, metals are really easy to do. Metals have the same name as the metal atom. So if I have a sodium ion, I just call it sodium. If I have a lead ion, I just call it lead. Okay? If I have a aluminium ion, I just call it aluminium. The name stays the same. So I'm going to underline that part. Same name. Okay? Next, non-metals, on the other hand, they change the ending of their name. And what they do is they change it to "ide." So an instance here, bromine, okay? Instead of bromine, I change it to bromide, okay? So the "ine" becomes an "ide." The suffix changes. Next, oxygen. The Y-gen, part of oxygen, so the "egen" becomes "ide." Again, every time we swap it for "ide." Sulfur, we get rid of the "fur" and it becomes sulfide. Okay? You're going to learn these three specifically. Okay? So, when we talk about the symbol and the valency, this is another way of saying the symbol and a charge. Okay? So what this means, if we look at copper 2, we start and we find copper on our periodic tables. Okay? And when you find copper, number 29, you will see that the symbol is Cu. Now, copper 2 tells us the charge. And copper, is it a metal or a non-metal? Metal. And it tells us the charge, so it's going to be 2+.
Can it be +2?
It sure can. But it needs to be written up the top right-hand corner. That's the only main rule here. Next one is iodide. Now, iodide ends in "ide", so it's going to be a non-metal. And if we have a look all the way over to element 53, you'll see iodine. If we get rid of the last part of iodine, it becomes iodide. And so iodide has the symbol of capital I, and iodide has a charge of 1-. And how we represent that is just a negative symbol. You don't need to write a 1.
Oh, never mind.
Now, how do you know the charge? You can look at your periodic table and you can see it's in the halogens, and you can see that above your periodic table you have the charge for all halogens, which is negative. Group 7. So, sodium ion now. We look for sodium, and you find sodium as element number 11. And so we go to sodium, Na, and we see that the charge for all elements in the first group of the periodic table is +1. Now, instead of writing +1, we can just write plus.
How do you know?
Question?
How do you know if it's
Never changes here.
Because you've written them on your periodic table. Yeah. Next. Next is chloride. So chloride, you can look for element number 17 on your periodic table. You can see chlorine. We've replaced the "ine" with "ide." And so the symbol for chloride is the same, Cl. And it is in the 7th group of the periodic table, which means, once again, it has a charge of -1. So we can just write it as a negative.
Do you have to do Roman numerals?
What?
Like,
For copper 2, yes, and we'll talk about that in a minute.
aluminium 3.
No. Yes.
Would you get marked docs if you didn't know the name for the I?
Yes.
So
We're going to work on this a lot. So when I said this was the final bit of content and we just practice it a lot, I really wasn't kidding. We are going to practice this a lot now. Next, potassium. You can look. Number 19, potassium has the symbol of K and the valency of 1+. Oxide, number 8, oxide has the symbol of O, 2-. Now, what I'm going to have you do is I want you to write down the name for each of these ions. Now, the good news for you, the only two with a different name will be each of these. I'm not going to say the name out loud. I want you to have a go. But both of them were in our examples up the top. All of the other metals, okay, keep their original name. So using your periodic table, can you go and write out the names for each of these metals and non-metals? Na+, as we discovered, this was a metal. So this metal is sodium. Al3+ is aluminium. I'm going to skip over C for a second, but we'll do the next one, which is zinc, then potassium, Now, when we get to copper, okay, copper has a unique rule because there's two different versions of copper. There's copper plus and there's copper 2 plus. Now, the one that we've given you is copper 2 plus. And so what we do next to it is we write the Roman numeral for 2. The next one, and you can see this example now, is iron. Because there are different versions of copper with different charges. So there's copper 1 and there's copper 2. The one that we can see really clearly now is if I fill in H and K, you can see that we have iron and iron. Now the difference is there's iron 2 plus and iron 3 plus. Iron 2 plus gets called iron 2 and iron 3 plus gets called iron 3. And we always write those numbers in Roman numerals. Okay. So our final metal was lead, and this is before we jump into the final two, which was bromine, which gets turned into bromide, and oxygen, which gets turned into oxide. So here's what I will have you do now. The very final thing for our lesson today. Final thing. This table below is our piecing together of all of the skills that we've been working on so far. So we're going to do magnesium together right now. If you're feeling confident though, please feel free to jump on. So, just do it again. Aluminium is in there twice and that's okay. So, number 1, I want you to look at magnesium on your periodic table. It has 12 protons and an atom of magnesium is going to have 12 electrons. We then look at the mass for magnesium and we see the mass is 24. We go 24 minus the atomic number 12 gives us 12 neutrons. Now, we've been told that in the electron configuration, okay, it has 12 altogether. That's made up of 2 in its inner shell, 8 in its second shell, and how many are left over? 2. This means for us, how many valence electrons are there? 2. And here is the final part. In order for magnesium to get a full shell, is it easier for it to gain 6 or to lose 2? And if it loses 2 of its negative electrons, it is going to end up with a charge of +2, the valency here. So you know what, we'll do one more together and then I'm going to leave them all to you. So aluminium, you turn to aluminium and you see that it is number 13. It has 13 protons, 13 electrons. What is the weight for aluminium? What is the mass? Sorry? 27. And we go 27 minus 13, which gives us 14. Now, the electron configuration, we have 13 electrons altogether, so we go 2, 8, and what is the leftover? 3. So again, I look for how many valence electrons there are, and I see that there are 3 valence electrons. Now, is it easier for magnesium to lose 3 electrons or gain 5? Lose 3. And if I lose 3 negative charges, what's my charge going to be? +3.